Okay, I needed a lot for this, but like I said, short of putting up crypto, local keys, public keys, private keys, in terms of the way of describing certain things, let's just put this away for right now.
This video is sponsored by Dashlane. Circuits and electronics, image processing, computer graphics,
For more on the
quantum
markets, let's bring in
mechanics,
Barry Knapp.
Google
He's
PageRank
managing partner
algorithm,
and director
any
of
kind of
research at
network,
Ironsides
other stuff.
Macroeconomics. And Barry,
These are the kinds of things where matrices are used and extremely important for understanding or analyzing different systems. And although I can't discuss everything in one video, this should give you some insight into the applications of matrices beyond what an introductory course might include. Now, in the beginning, matrices can be one of the most boring subjects we learn in math. Maybe not for everyone, but at least that's how it was for me. I mean, we're told, hey, here's how matrix addition works.
Real close to each other.
The corresponding entries.
Remember some of the hydrogen bond stuff, like loops and black bodies coming across one quadrant from X to Z, quantifying Y.
But when it comes to matrix multiplication, we do this weird row by column.
You get different versions of this. 1 is 2, 2 is 3, but if you factor on those scales, you'll have a daily macro or a monthly macro to the yearly max, 0, 1.
You might learn more in high school,
From there to here, based on the first time calculus form.
However, I promise matrices are used way more than you probably think. But the first thing we need to realize is that matrices do things to vectors. Don't take this as a definition, because it's obviously not. But we do need to see what happens when we multiply
Different
a
ways to
matrix
look at those
by a
things.
vector.
And they might come up in
For
position.
example, a vector that starts at the origin and ends at 1, 1 can be written in matrix form as shown.
Dow Jones, Dow Industrial, right? One of them that does that under that sector of things where it could be a pain in the ass depending on how you want to look at Dow. Dow Industrial, finance, economics. S&P 500.
So we put a vector
Also,
in, and the
A1,
matrix scaled
A2,
and
same thing,
rotated
gluon,
to get a new
photon,
vector out.
does the same thing different, M1 to
This is
M2,
what I mean by the
F1 to F2
matrix
minus
doing
F1,
things
so
to the
stay in
vector.
space,
And in this case,
continue,
different inputs will be
things like
rotated and
continue.
scaled differently, which we'll see in a second.
And you get 10-year notes
Now,
that
some
look the
matrices
same
are
way,
much simpler.
based on,
like this one here
watch
just
Pretty Money.
rotates. Put a vector in, aka multiply by the matrix, and out will come the same vector rotated 90 degrees counterclockwise. This matrix, on the other hand, will just scale. Any vector that goes in comes out twice as long.
So then you get into some of this
2 by 2
fancy
matrices
bullshit.
like this one we were analyzing aren't as simple. Different input vectors, I'll just put a few here as an example, get scaled and rotated differently. However, the transformations are all linear, as in any vector on the same line as one of those inputs will be mapped to a vector on the same line as the corresponding outputs.
This is a very tight
These linear
sequence. This is
transformations
like
are why we call the
at the
first
quantum
in-depth
limit
class on
of being a
matrices
diode,
linear
an
algebra.
LED. It might.
Anyways, I'm going to redo those transformations once more, but this time pay attention to this vector here. You'll notice it's the only one that is just scaled. It doesn't rotate at all. And this would happen to any vector on that same line because of what we just saw. Any vector that is only scaled by a matrix is called an eigenvector of that matrix. And how much the vector is scaled by, or 2 in this case, since the length of the plane, will be known as the eigenvalue class transform plot. And if we actually use a third dimension for those
It is
matrices,
here on Earth, doing this. These are the black holes. You can cut that into a cell that looks like.
This plane here shown in green, which I'll fade the plot a little so you can see, is all the inputs S. X represents alpha, and Y is really I omega. The 3D plot itself is the magnitude.
Yes, how do I know these things?
This is the Laplace transform of the original function e to the minus t sine of t. The thing is, this doesn't tell us much just by looking at it. So what I'm going to do is graph the equation alpha or x equals 0 that'll give us a plane as shown. Because remember, from before, the alpha equals 0 line actually yields the Fourier transform of the original function, which we can see with the intersecting curve.
We have resurfaced high-quality masks, if you notice.
This is what I meant by the Fourier transform is a
Let's
slight
use this to look at it.
Resurfaced and kind of doubled up on that
But now I'm going to decrease alpha while also plotting the original function times e to the minus alpha t.
In a higher quality mask, and I think that's
right now alpha is 0, so that exponential is just 1. But as I sweep alpha, we start to see both plots change. And what you're seeing with that intersection on the right is the Fourier transform of the plot on the left.
Somewhere around in here he's floating. There's one here, there's
like here, I'll posit alpha
somewhere
equals
around in
negative
here
0.5.
floating around,
This
I'm
is what we
sure.
just saw a minute ago, where the original curve
Maybe he's
times
upside down right now.
positive 0.5t, because that double negative has a Fourier transform with those two small